What is everything made of? Stars, planets, people, even the air around us. For thousands of years, humans have searched for the smallest pieces of reality. We discovered atoms. Then we discovered that atoms themselves contain smaller particles. And eventually, we found something even deeper. A collection of fundamental particles that, as far as we know, cannot be broken down any further. Together, they form the foundation of the Standard Model of particle physics. But what exactly is the Standard Model? An atom is made of a nucleus surrounded by electrons. The nucleus contains protons and neutrons. But even protons and neutrons aren't fundamental. Zoom inside them, and we find quarks. So the deeper we look, the more elementary the universe becomes. The Standard Model describes the known fundamental particles and the forces that govern how most of them interact. It is our best-tested theory of the microscopic universe. At the heart of the Standard Model are two major families of matter particles, quarks and leptons. There are 6 types of each. For quarks, up, down, charm, strange, top, bottom. And for leptons, electron, muon, tau, along with 3 corresponding neutrinos. These particles come in 3 generations. The first generation contains the particles that make up ordinary matter around us. The heavier generations are unstable and eventually decay into lighter particles. Quarks don't normally exist by themselves. They are bound together by one of the fundamental forces of nature, the strong nuclear force. 3 quarks can combine to form particles such as protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. And the particles responsible for the strong force are called gluons. They act as the messengers of the strong interaction. Another fundamental interaction is the electromagnetic force. It governs interactions between electrically charged particles, and its messenger particle is the photon. Photons are the particles of light. They are responsible for everything from radio waves to visible light to X-rays and gamma rays. So the same fundamental particle that carries light also carries the electromagnetic interaction. There is another force in the Standard Model, the weak nuclear force. It is responsible for processes such as certain forms of radioactive decay. It can even transform one type of particle into another. The weak interaction is carried by 3 particles, the W+, the W, and the Z boson. Unlike the photon, these particles are massive. And because they are so massive, the weak force operates only over extremely short distances. So we now have matter particles and force-carrying particles. But something is missing. Why do some fundamental particles have mass? And why do others behave as if they have no mass? The answer leads us to one of the most remarkable ideas in modern physics, the Higgs field. The Higgs field is thought to fill all of space. Elementary particles interact with this field to different degrees. That interaction contributes to their masses. And the particle associated with the Higgs field is the Higgs boson. In 2012, experiments at CERN's Large Hadron Collider discovered a particle consistent with the Higgs boson. It was a major confirmation of the mechanism behind electroweak symmetry breaking. Put everything together, and the Standard Model becomes a remarkable map of the microscopic universe. 6 quarks, 6 leptons, 4 gauge bosons associated with the electromagnetic, weak and strong interactions, and the Higgs boson. But there is an important catch. The Standard Model does not describe everything. Gravity is missing. The Standard Model successfully describes 3 fundamental interactions: the strong force, the electromagnetic force, and the weak force. But gravity is described by Einstein's general relativity, not by the Standard Model. We still don't have a complete, experimentally confirmed quantum theory of gravity. And there are other mysteries. The Standard Model doesn't explain the nature of dark matter. It doesn't explain dark energy. And although neutrinos are included in our understanding of particle physics, the simplest original version of the Standard Model treated them as massless. We now know that neutrinos have tiny masses. This tells us that the Standard Model, in its original form, is not the final story. Yet despite these limitations, the Standard Model is astonishingly successful. Scientists have tested its predictions in particle accelerators around the world. Particles collide at enormous energies. New particles are produced, their properties are measured, and the results repeatedly agree with the theory to extraordinary precision. The Standard Model isn't simply a list of particles. It is a mathematical framework describing how those particles interact. So, what is the Standard Model? It is our best current description of the fundamental particles and 3 of the 4 known fundamental interactions. It tells us what ordinary matter is made of. It explains how particles interact. It predicted new particles before they were discovered. And it has survived decades of incredibly precise experimental tests. But it is not the end of physics. Somewhere beyond the Standard Model may lie answers to some of our deepest questions. What is dark matter? Why do neutrinos have mass? Why is there more matter than antimatter? How does gravity fit into quantum physics? And is there a deeper theory connecting everything together? The Standard Model may not be the final blueprint of reality, but for now, it is one of the greatest maps humanity has ever created. A map of the smallest known pieces of the universe and the strange rules that make them interact.